Derivatives of trig functions, part 2. Recall these trigonometric limits that you should memorize, because we will be applying them today, in order to evaluate more complicated limits. Remember that the goal is to get the angle and your numerator or denominator to match each other. We have the limit as x approaches 0 of sine of 5x over sine of 2x. So we'll want to split these two limits up. So we have the limit as x approaches 0 of sine of 5x over 1 times the limit as x approaches 0 of 1 over sine of 2x. And we need our 5x and that denominator to match, and that 1 and the 2x to match. So we'll multiply this first limit, which is really just multiplying the whole thing, by 5x over 5x. And we'll multiply this second limit by 2x over 2x. This 5x will go along for our limit, while the 5x in the numerator is kind of left over. This 2x will help us evaluate this limit, while the 2x in the denominator is left over. So now we have the limit, and that kind of looks like limit, so hold on. The limit as x approaches 0 of our leftovers, so our 5x over 2x, times the limit as x approaches 0 of sine of 5x over 5x times the limit as x approaches 0 of 2x over sine of 2x. When we look at the limit as x approaches 0 of 5x over 2x, our x's will divide out, so this limit will be equal to 5/2 times the limit as x approaches 0 of sine of 5x over 5x is one of those known limits, times the limit as x approaches 0 of 2x over sine of 2x is another known limit, which also evaluates to 1. So we have 5/2 times 1 times 1, which is equal to 5/2. So that is what our limit evaluates to. We have the limit as x approaches 0 of sine of 3x times sine of 7x over x squared. Now x squared is the same thing as x times x. So we can split this x up because our sine of 3x will need an x, and our sine of 7x will also need to be divided by an x. So this is equal to the limit as x approaches 0 of sine of 3x over x times the limit as x approaches 0 of sine of 7x over x, where these x's came from our x squared. Now we need to get our angle and our denominator to match for each of these. So we need to multiply sine of 3x over x by 3 over 3, because there's already an x there. And we need to multiply sine of 7x by 7 over 7. This 3 is going to help us evaluate our limit, while the 3 in the numerator is left over. This 7 is going to help us evaluate our limit, while the 7 in the numerator is left over. Since we don't have any leftover variables, we can just pull out our leftover constants. So that's 3 times 7 times the limit as x approaches 0 of sine of 3x over 3x times the limit as x approaches 0 of sine of 7x over 7x. So that will be equal to 21 times each of these limits. The limit as x approaches 0 of sine of 3x over 3x is one of our known limits. It evaluates to 1. And let me replace these brackets. It actually doesn't make a difference, but I just think this looks cleaner. The limit as x approaches 0 of sine of 7x over 7x is also a known limit that evaluates to 1. So our overall limit is 21 times 1 times 1, which is equal to 21. We have the limit as x approaches 0 of sine of 5x over 5x cubed minus 4x. Whenever you can factor and you're evaluating a limit, it's a good idea to try out factoring. So we have the limit as x approaches 0 of sine of 5x over x times 5x squared minus 4, because x is a common factor between 5x cubed and 4x. Now we can split up some of these factors, so this will be equal to the limit as x approaches 0 of, let's pull out our sine of 5x. In order to evaluate this, we'll need a 5x in the denominator. We already have this x. Then we have the limit as x approaches 0 of 1 over 5x squared minus 4. To evaluate the limit as x approaches 0 of sine of 5x over x, we'll need these to match. So the x in the denominator is missing our 5, and we'll multiply by 5 over 5 to fix that issue. This 5 will help us evaluate our limit. This 5 is left over. So this will be equal to 5 times the limit as x approaches 0 of sine of 5x over 5x times, well, let's try out direct substitution for this next piece. So that'll be 1 over 5 times 0 squared minus 4. So we have 5 times, this is one of our known limits, and we'll evaluate to 1, times 1 over 5 times 0 minus 4 gives us 1 over negative 4. So we have 5, well, negative 5/4. We have the limit as x approaches 0 of x times sine of 1 over x. The first thing we'll want to do is try to write this as a quotient. A common trick that you'll want to use over and over in calculus is that if you're multiplying by x is equivalent to dividing by 1 over x. So this is equal to the limit as x approaches 0 of sine of 1 over x divided by 1 over x. And now this actually works out pretty well. These guys match each other, so this limit evaluates to 1.